Welcome to day 10. Yesterday, we explored generative AI and large language models, understanding how these systems learn to create. Today, we take those technical foundations and see how AI transforms specific industries and domains. AI is no longer theoretical. It's deployed in hospitals making diagnostic decisions, in vehicles navigating streets, in financial systems making trading decisions, in laboratories discovering new drugs. Today, we explore real world impact. We'll study healthcare AI, how models analyze medical images, assist diagnosis, and accelerate drug discovery. We'll examine autonomous vehicles, the most complex AI systems deployed in the real world, handling perception, planning, and decision making under uncertainty. We'll explore financial AI, trading algorithms, fraud detection, risk modeling. We'll see scientific AI, from AlphaFold predicting protein structures to materials science optimization. Each domain presents unique challenges. Healthcare requires extreme reliability because errors have life and death consequences. Autonomous vehicles must ensure safety in unpredictable environments. Finance faces adversarial actors exploiting any vulnerability. Science demands reproducibility and correctness. By understanding domain specific applications, you'll see how abstract AI concepts translate to real impact and understand deployment complexity. Let's explore AI's transformative power. Here's exactly what we'll accomplish today, seeing how AI applies across domains. First, we'll explore healthcare AI. How do models analyze medical images, X rays, CT scans, MRI images to detect anomalies? How do diagnostic systems augment physician decision making? How do models accelerate drug discovery by predicting molecular properties? Healthcare AI demonstrates how AI can directly save lives while creating new ethical challenges. Second, we'll master autonomous vehicles, perhaps the most complex AI systems deployed. They must perceive environments through cameras, LiDAR, radar, plan safe trajectories, make real time decisions under uncertainty, handle edge cases and adversarial scenarios. Understanding autonomous vehicles reveals challenges in building robust, safe AI systems in complex, real world environments. Third, we'll explore financial AI. How do trading algorithms make decisions at millisecond scales? How do fraud detection systems identify suspicious patterns? How do risk models predict market behavior? Financial AI reveals challenges in building systems that face intelligent adversaries. Fourth, we'll see scientific AI. AlphaFold's breakthrough in protein structure prediction, generative models designing new materials and molecules, AI accelerating scientific discovery across domains. Fifth, we'll understand that domain specific expertise is crucial. Each domain has unique requirements, constraints, and challenges. Generic AI rarely works directly. Successful deployment requires deep domain understanding. Healthcare represents one of AI's most impactful and promising applications. AI can save lives, improve outcomes, and accelerate discovery, but healthcare also demands extreme care. Errors have severe consequences. Medical imaging analysis. Radiologists interpret thousands of images daily. AI can analyze images to detect tumors, fractures, infections, and anomalies. Some AI systems achieve radiologist level accuracy. Importantly, AI often makes different mistakes than radiologists. They catch different anomalies. AI and human radiologists together are more accurate than either alone. Clinical decision support. AI systems analyze patient data, symptoms, lab results, medical history to suggest diagnoses and treatments. These systems augment physician judgment, providing another perspective. In practice, clinicians make final decisions using AI as a tool. Drug discovery is slow and expensive. Testing millions of candidates takes years and billions of dollars. AI models predict whether candidate molecules will be effective, toxic, or have desirable properties. This dramatically reduces candidates to test experimentally, accelerating discovery. Disease risk prediction identifies high risk patients proactively. AI analyzes patient records to predict who will develop diabetes, heart disease, or other conditions. Enables preventive interventions, treatment personalization, patient specific factors, genetics, microbiome, lifestyle affect treatment response. AI helps personalize treatments for individual patients. Healthcare AI demonstrates AI's potential for positive impact, but also challenges in deployment. Autonomous vehicles represent perhaps the most complex AI systems deployed in the real world. They must perceive, reason, and act in unstructured, unpredictable environments while ensuring safety. Perception is extremely challenging. Multiple sensors provide different information. Cameras provide rich visual data but struggle in poor lighting and reflections. LIDAR provides 3D point clouds but has limited range and weather sensitivity. Radar detects moving objects reliably but provides sparse data. The system must fuse these diverse sensor streams, handle sensor failures, and detect objects with high accuracy. Localization requires determining vehicle position with meter or sub-meter accuracy. GPS is sometimes unreliable in urban canyons or tunnels. Vision-based localization uses map matching. Maintaining accurate localization enables safe planning. Planning involves predicting how other traffic participants will move, avoiding collisions, following traffic rules, and minimizing travel time. This requires reasoning about uncertainty. Will that pedestrian cross? Will that car change lanes? Plans must be conservative. Assume worst case for safety. Control executes plans precisely. Steering, acceleration, braking must be smooth and accurate despite vehicle dynamics and road conditions. Safety is paramount. Edge cases are infinite. What about a traffic cone in the middle of the lane? What if a sensor fails? Autonomous vehicles must handle failures gracefully. Testing in simulation is extensive, but real world deployment introduces scenarios never seen in testing. Autonomous vehicle perception is AI's most demanding real time challenge. Systems must process terabytes of sensor data per day, detecting objects, understanding scenes, building 3D maps, all in real time with high accuracy. Object detection identifies vehicles, pedestrians, cyclists, traffic signs, obstacles. These must be detected reliably in all lighting conditions, weather, occlusion. The system tracks objects across frames, predicting trajectories. Missing a pedestrian is catastrophic. Semantic segmentation classifies pixels into categories: drivable road, lane markings, sidewalk, grass, sky. Instance segmentation distinguishes individual objects of the same category. This enables understanding scene structure, crucial for planning safe trajectories. 3D reconstruction builds a 3D map of the environment. LiDAR directly provides 3D point clouds. Vision-based methods reconstruct 3D structure from 2D images. This 3D understanding is crucial for predicting trajectories and planning collision-free paths. Sensor fusion combines information from diverse sensors. Each sensor has different strengths and weaknesses. Fusing them provides robust perception. Modern systems use deep learning to learn optimal fusion strategies. Real-time processing is critical. Autonomous vehicles operate at highway speeds where millisecond delays matter. Processing must be fast enough for real-time decision-making. This constrains model complexity and inference latency. Financial AI operates at scale and speed unmatched in other domains. Trading algorithms make microsecond decisions on billions of dollars. Fraud detection systems must identify criminal activity in milliseconds. Risk models inform trillion-dollar investment decisions. Algorithmic trading processes market data and executes trading decisions automatically. Some algorithms trade based on technical indicators, news, or market microstructure. Others use machine learning to detect patterns. Speed matters tremendously. Microsecond advantages matter at scale. This creates incentives for sophisticated techniques and raises fairness questions about whether human traders can compete. Fraud detection is a classic ML application. Systems flag suspicious transactions for human review. They learn patterns of fraudulent versus legitimate transactions. Challenges include concept drift. Fraud patterns evolve as criminals adapt. Imbalanced classes, fraud is rare, making detection difficult. Privacy concerns? Monitoring transactions raises privacy questions. Credit risk modeling predicts default probability. Banks use scores to decide loan approval and interest rates. These scores influence whether people can borrow for homes, education, businesses. AI in financial decisions raises fairness and discrimination concerns. Biased models perpetuate inequality. Portfolio optimization allocates capital to maximize returns while managing risk. Modern portfolio theory and machine learning enable sophisticated optimization, but past performance doesn't guarantee future results. Markets face unprecedented scenarios. Time series forecasting predicts market movements. Markets are notoriously difficult to forecast. They're partially driven by random events and sentiment. ML provides tools, but not magic. AlphaFold represents one of AI's greatest achievements, solving a fundamental problem in biology that stumped scientists for decades. Proteins are chains of amino acids that fold into 3D structures. Structure determines function. Understanding structure is crucial for medicine. Many diseases involve misfolded proteins. For 50 years, determining protein structures required expensive lab work. X-ray crystallography, cryo-EM. Processing thousands of proteins took years and millions of dollars. Computational prediction failed because the search space is enormous. A protein can fold into trillions of configurations. AlphaFold used deep learning on evolutionary data. Natural evolution explores structure space over millions of years. By learning patterns from sequence variations across species, AlphaFold learned structure constraints. The model predicts 3D coordinates for each atom, achieving accuracy matching experimental methods. The impact is extraordinary. AlphaFold predicted structures for hundreds of millions of proteins, essentially all known proteins. This accelerates biology across domains. Drug discovery benefits tremendously. Understanding protein structures accelerates rational drug design. Disease research benefits. Structural insights reveal disease mechanisms. Evolutionary biology benefits. Structures reveal evolutionary relationships. AlphaFold demonstrates that deep learning can solve fundamental scientific problems. It shows AI's potential to accelerate discovery. Similar approaches are being applied to molecular design, chemical reactions, materials properties. The message is clear: AI is transforming scientific discovery. Drug discovery traditionally takes 10-15 years and costs billions. AI can dramatically accelerate this process by computationally exploring molecular space. Molecular generation uses generative models to create candidate molecules. Given desired properties, models generate molecules likely to have them. This replaces tedious manual design with automated generation. Property prediction. Once generated, predict whether candidates have desired properties. Will the molecule be effective, toxic, bioavailable? Models trained on experimental data predict properties for new candidates. This enables filtering vast numbers of candidates before expensive experimental testing. Virtual screening explores billions of candidate molecules computationally. Traditional screening tests millions experimentally, expensive and slow. Computational methods score candidates, identifying promising ones for experimental validation. Structure activity relationships reveal what chemical features make drugs effective. Models learn which molecular structures bind to disease targets, cause desired effects, avoid toxicity. This knowledge guides design of new drugs. Multi-objective optimization balances competing objectives. Ideal drugs are effective but not toxic, easily absorbed but not metabolized too quickly, manufacturable but expensive to produce. Optimization finds candidates balancing these trade-offs. AI dramatically accelerates drug discovery. What previously took years now takes months. Diseases affecting small populations, historically neglected because development costs exceed potential market, become viable for AI assisted discovery. The impact on global health is profound. Recommendation systems are everywhere. Netflix, Amazon, YouTube, Spotify. They decide what content billions of people see daily. They shape information access and cultural consumption. Collaborative filtering. Users with similar preferences tend to like similar items. If user A and B rated movies similarly and A rated movie X highly, recommend X to B. This requires no content understanding, just preference patterns. Works well, but struggles with new users and items. Cold start problem. Content-based filtering recommend items similar to ones the user liked. If user liked action movies, recommend similar action movies. This requires understanding item features and content. Works well for new items but less effective at discovery. Recommends more of what user already likes. Hybrid approaches combine signals. Popularity, recommend what's popular. Personalization, recommend for user specifically. Diversity, recommend variety. Novelty, recommend new items. Balancing these objectives is crucial. Over-personalizing creates filter bubbles where users see only content matching existing preferences. This limits discovery and can amplify polarization. Deep learning learns complex user-item relationships. Neural networks can capture subtle interaction patterns, but they require vast data and computing resources. Only large companies can train state-of-the-art recommendation systems. Recommendation systems reach billions of people daily. They influence what content people consume, what products they buy, what information they access. They're tremendously powerful and raise important questions about filtering, polarization, and diversity. Material science benefits tremendously from AI. Discovering new materials with desired properties traditionally requires extensive experimentation. AI enables computational exploration of vast material space. Crystal structure prediction. Given chemical composition, predict the 3D crystal structure and properties. This requires understanding quantum mechanics at scale. Deep learning models trained on experimental data learn structure patterns, enabling prediction for new compositions. Generative design, specify desired properties and generate candidate materials. Want a material that's lightweight, strong, thermally conductive? Generate candidates matching specifications. This automates material design. Property forecasting. Predict material properties without experimental synthesis. Will this alloy be strong, ductile, corrosion resistant? Models predict properties, enabling screening vast numbers of candidates. Battery optimization. Design batteries with higher energy density, longer lifespan, better safety. These are crucial for electric vehicles and renewable energy storage. AI accelerates discovery of new battery chemistries and architectures. Photovoltaic optimization. Improve solar cells and other photovoltaic materials. More efficient photovoltaics accelerate renewable energy adoption. AI helps discover new materials and optimize designs. The impact is profound. New materials enable new technologies. Better batteries enable electric vehicles and energy storage. Better solar cells accelerate renewable energy. Better semiconductors enable advanced computing. AI accelerating materials discovery cascades through technology. This demonstrates how AI in one domain amplifies impacts across many domains. While AI demonstrates tremendous potential across domains, real world deployment faces substantial challenges. Data availability. Some domains have limited data. Rare diseases have few cases. Specialized industrial processes generate limited data. Small companies can't collect large data sets. Data limitations constrain AI development. Transfer learning and few shot learning help but aren't panaceas. Interpretability. In high stakes domains, decision makers need to understand why AI makes recommendations. Doctors need to understand diagnostic AI recommendations. Judges need to understand predictive policing. Black box models are unacceptable. Interpretability versus accuracy trade offs are challenging. Safety and reliability, errors are costly. Autonomous vehicle mistakes cause accidents. Medical misdiagnoses harm patients. Financial fraud causes losses. Safety requirements demand extreme reliability, robustness to distribution shift, and graceful failure handling. This is fundamentally harder than optimizing accuracy on test sets. Regulatory compliance. Healthcare, finance, and autonomous systems are heavily regulated. Deployment requires regulatory approval. Privacy regulations like GDPR restrict data use. Compliance adds complexity and cost. Integration. Deploying AI into existing systems is complex. Healthcare systems have legacy infrastructure. Finance has complex operations. Autonomous vehicles must integrate with existing transportation infrastructure. Integration challenges often exceed technical AI challenges. These challenges mean that deploying AI successfully requires much more than AI expertise. It requires domain expertise, regulatory knowledge, integration skills, and organizational change management. Each domain has unique ethical considerations. Understanding domain specific ethics is crucial for responsible AI development. Healthcare, patient welfare is paramount. AI should augment physicians, not replace them. Patients deserve informed consent and explanation. Privacy is critical. Medical data is highly sensitive. Allocation questions arise. How do we ensure AI assisted healthcare benefits everyone, not just wealthy populations? Autonomous vehicles. Responsibility for accidents is unclear. If an autonomous vehicle causes an accident, who's liable? The manufacturer, the owner, the software developer? How should autonomous vehicles make life and death decisions in unavoidable accidents? These questions are active policy debates. Finance. Historically, lending discrimination was explicit. Deny credit based on race or gender. Modern discrimination is implicit. AI amplifies historical biases encoded in data. Ensuring fairness in lending is crucial for opportunity and justice. Science. AI can make false discoveries. Models trained on biased data can perpetuate biases. Pressure to publish can incentivize overstated claims. Science requires rigor and reproducibility. AI threatens reproducibility if details of AI systems, training data, and processes aren't transparent. All domains share common themes: transparency about AI limitations, respecting user autonomy, considering power dynamics, and ensuring benefits are widely shared, not concentrated. Ethics isn't an afterthought, it should guide development from the start. A crucial lesson from specialized AI applications: domain expertise is absolutely critical. Generic AI rarely works directly. One of the biggest mistakes in AI is assuming domain specialists are unnecessary. It's tempting to think, collect data, train a model, deploy, but domain specialists understand constraints, requirements, and edge cases that generic ML practitioners miss. A radiologist knows what looks suspicious in medical images. A physicist knows which material properties matter most. A trader knows market microstructure. Effective AI teams combine domain experts with AI experts. Domain experts contribute understanding of what problems matter, what's realistic, what matters for impact. AI experts contribute technical skills in building systems. Together, they're far more effective than either alone. Domain-specific datasets, features, and evaluation metrics are crucial. Generic benchmarks often don't capture domain requirements. A model that's 99% accurate might be useless if the 1% of errors occur in critical cases. Domain experts know what accuracy on what metrics matters. Successful deployment requires deep domain understanding. How does this AI fit into existing workflows? What human AI collaboration looks like? What failure modes are acceptable? What's realistic given budget and constraints? These questions require deep domain knowledge. The lesson: if working in a specialized domain, spend time understanding the domain. Talk to domain experts. Learn what matters. This investment pays dividends in building systems that actually work and matter. As AI matures, several trends are democratizing access to advanced capabilities. Foundation models like GPT, BERT, and Vision Transformers are general purpose models trained on massive data. These models can be adapted to new domains with relatively little data. This reduces barriers to entry. Smaller companies and less wealthy institutions can leverage capabilities previously accessible only to tech giants. Transfer learning enables efficient adaptation. Pre-train on large general dataset, fine-tune on domain-specific data. This dramatically reduces data and compute requirements. A startup can build competitive healthcare AI without training from scratch. Open source tools democratize access to advanced techniques. PyTorch, TensorFlow, and countless specialized libraries mean building sophisticated AI systems is more accessible than ever. These trends mean many domains will see AI adoption that couldn't previously. But the critical lesson remains: successful deployment requires domain specific understanding. AI techniques are democratizing, but domain expertise remains essential. The future favors teams that combine both. Tomorrow is day 11, building AI systems in production. We shift from applications to the systems engineering required to deploy AI reliably at scale. Today, we've seen AI transforming domains: healthcare, autonomous vehicles, finance, science. But the presentations hide immense complexity. How do you actually build these systems? How do you manage data pipelines? How do you train models reliably? How do you monitor systems in production? How do you handle model degradation over time? Tomorrow, we explore production ML, the engineering required to move from research prototypes to deployed systems serving millions of users. We'll cover end-to-end pipelines from data collection through deployment. We'll discuss data engineering, feature engineering, model training at scale, and monitoring. Production ML is where most AI work happens. Research papers get attention, but most AI practitioners build systems. Understanding production ML is crucial for real-world impact. Excellent work today. You now understand how AI transforms healthcare, autonomous systems, finance, and science. You appreciate domain-specific challenges and why domain expertise matters. You understand that successful AI requires combining technical skill with deep domain knowledge. See you tomorrow as we explore the engineering required for production AI systems.